Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Zakon Galiputra Sumarna, and today I would like to make a video about English for Physics second assignment taught by Mr. Nurul Hidayat. So before we start to read, we started with Bismillahirrahmanirrahim. So 1, 2, 3, Bismillahirrahmanirrahim. Section 2.6, Analysis Model, Particle under constant acceleration. If the acceleration of a particle varies in time, its motion can be complex and difficult to analyze. A very common and simple type of one-dimensional motion, however, is that in which the acceleration is constant. In such a case, the average acceleration AX average over any time interval is numerically equal to the instantaneous acceleration AX at any instant within the interval, and the velocity changes at the same rate throughout the motion. This situation occurs often enough that we identify it as an analysis model, the particle under constant acceleration. In the discussion that follows, we generate several equations that describe the motion of a particle for this model. If we replace a x average by ax in equation 2.9 and take ti equals 0 and tf to be any later time t, we find that formula as ax equals vxf minus vxi over t minus 0, or vxf equals vxi plus axt for constant ax. This powerful expression enables us to determine an object's velocity at any time t if we know the object's initial velocity vxi and its constant acceleration ax. A velocity time graph for this constant acceleration motion is shown in figure 2.11b. The graph is a straight line, the slope of which is the acceleration ax. The constant slope is consistent with ax equals dvx over dt being a constant. Notice that the slope is positive, which indicates a positive acceleration. If the acceleration were negative, the slope of the line in figure 2.11b would be negative. When the acceleration is constant, the graph of acceleration versus time in fig 2.11c is a straight line having a slope of 0. Because velocity at constant acceleration varies linearly in time according to equation 2.13, we can express the average velocity in any time interval as the arithmetic mean of the initial velocity vxi and the final velocity vxf, or vx average equals vxi plus vxf over 2 for constant ax. Notice that this expression for average velocity applies only in situation in which the acceleration is constant. We can now use equation 2.1, 2.2, and 2.14 to obtain the position of an object as a function of time, recalling that delta x in equation 2.2 represents xf minus xi, and recognizing that delta t equals delta tf minus ti equals t minus 0 equals t. We find that formula as xf minus xi equals vx average t equals a half multiplied by vxi plus vxf multiplied by t. xf equals xi plus a half multiplied by vxi plus vxf multiplied by t for a constant ax. This equation provides that the final position of the particle at time t in terms of the initial and final velocities. We can obtain another useful expression for the position of a particle under constant acceleration by substituting equation 2 2.13 into equation 2.15. So the formula was xf equals xi plus a half square bracket vxi plus vxi plus axt square bracket multiplied by t. xf equals xi plus vxit plus a half axt square for constant ax. This equation provides the final position of the particle at time t in terms of the initial position, the initial velocity, and the constant acceleration. The position time graph for motion at constant positive acceleration shown in figure 2.11a is obtained from equation 2.16. Notice that the curve is a parabola, that the slope of the tangent line to this curve at t equals 0 equals the initial velocity vxi, and the slope of the tangent line at any later time t equals the velocity vxf at that time. And finally, we can obtain an expression for the final velocity that does not contain time as a variable by substituting the values of t from equation 2.13 into equation 2.15. And the formula, which is xf equals xi plus a half multiplied by vxi plus vxf multiplied by vxf minus vxi over ax equals xi plus vxf square minus vxi square over 2ax. So the equation, which is vxf square equals vxi square plus 2ax multiplied by xf minus xi for constant ax. This equation provides the final velocity in terms of the initial velocity, the constant acceleration, and the position of the particle. For motion at zero acceleration, we see from equations 2.13 and 2.16 that vxf equals vxi equals vx, xf equals xi plus vxt when ax equals 0. That is, when the acceleration of a particle is 0, its velocity is constant, and its position changes linearly with time. In terms of models, when the acceleration of a particle is 0, the particle under constant acceleration model reduces to particle under constant velocity model, section 2.3. The equation 2.13 through 2.17 are kinematic equations that may be used to solve any problem involving a particle under constant acceleration in one dimension. These equations are listed together for convenience on page 38. The choice of which equation you use in a given situation depends on what you know beforehand. Sometimes it is necessary to use two of these equations to solve for two unknowns. You should recognize that the quantities that vary during the motion are position xf, velocity vxf, and time t. You will gain a great deal of experience in the use of these equations by solving a number of exercises and problems. Many times you will discover that more than one method can be used to obtain a solution. Remember that this equation of kinematics cannot be used in a situation in which the acceleration varies with time. They can be used only when the acceleration is constant. So that is my reading text assignment for English for Physics assignment taught by Mr. Nurul Hidayat. Thank you very much, thank you so much. And for the last, wassalamualaikum warahmatullahi wabarakatuh.